Hello dear students, welcome you all for transmission and distribution class. In the previous class, we have seen the short transmission line. So the first part of the transmission lines classification, that is the below 50 kilometers, usually we are calling it as a short transmission line, where we have seen that sending end voltage and receiving end voltage. In the short transmission line, the thing is what? The sending end current is same as the receiving end current because of there is no capacitance in between. We are neglected the capacitive effects, only resistance and inductive reactance is taken. That's what Vs can be written as there Vr plus Iz. Okay, and IAS is equal to IR only. Means sending end current is same as the receiving end current. But coming to the medium transmission line, now we need to take the effect of the capacitance. So usually this is more than the 20 kilowatt, and however the length is usually taken from 50 to 150 kilometer. So as the length is bigger than the short transmission line, so usually operating voltage is also more than the short transmission line. In order to obtain the reasonable accuracy, we need to take the calculation of the capacitance also. So the capacitance is uniformly distributed over the entire line. Okay. However, in order to make the calculation simple, the line capacitance are assumed to be lumped or concentrated at any point. Okay. Usually, as the resistance, inductance, and capacitance is distributed uniformly, because that's what only the value is given per kilometer. But for having the easiness in the calculation, we are considering the capacitance at any one point or any 2 points, like dumped at somewhere. Okay, so this is helps us the calculating the all the currents and performances easily at a particular point. So the thing is what, where to locate or where to lump the total capacitance. So from the starting point to end point, uniformly capacitance is distributed. Where to calculate which point? So depending upon the calculation of the capacitance point, the medium transmission lines are further classified in three different ways. That is, first one is end condenser method, second one is nominal T method, third one is nominal phi method. Here three different methods are used. Means end condenser method means total capacitance are taken at the receiving end side, at the end. That's why it is called as end condenser method. Condenser method. Second one is nominal T method. Nominal T method is such the way that the total capacitance are taken at the center point of the line. And nominal phi method is we are having the total capacitance in exact half. Means if total capacitance is C, we will be having C by 2, C by 2. First half is at the sending end, next half is at the receiving end. So it looks like a phi in mathematics. So it is called as nominal phi method. So three different methods are used. Let us have the first end condenser method. You can see the figure 10.8, which shows the transmission line with the medium transmission line of end condenser method, where sending end voltage is Vs, sending end current is Is, resistance is the total resistance of the line, XL is the total inductive reactance of the line, where C is the total capacitance which is taken at the load side. Because of that, a current IC flows in the capacitance C, and IR is the current which flows in the load. That's what that current is called as receiving end current, and the voltage across the load is called as VR. It is very clear that compared to your short transmission line, there both IS is IR are same, because the same current which is coming from the sending end is flowing in the load, but here not the exact current which is coming from the sending end current will not flow in the load. The part of the current is flowing in the capacitance. That's what receiving end current is having different value than the sending end current. So voltage across the load is called as receiving end voltage. So that is the same thing I have explained here. Let IR is equal to load current per phase. Actually, this is a single phase equivalent model we have taken here. Fine. Now we will see the phasor diagram here. Anyhow, we used to take the VR as the reference, because the receiving end power is receiving end voltage is taken as the reference here. This figure 10.9 shows us the vector diagram. See, if VR plus J0, that is at the 0, means we are taking VR as the reference. Load current IR is what? Actually IR cos phi r minus J phi r, we are knowing. And assuming that the load is a RL, obviously IR is having lagging with the voltage. That's what we will be writing here IR is having an angle phi r with the VR. You can see in this figure it is very clearly. IR is having an angle phi r with the VR. Okay. And what is the actual capacitive current IC? We know that capacitive current is given by JV omega C. Actually that is what V by XC, or XC is nothing but 1 over J omega C. That's what it is directly given by JV omega C. V is receiving end voltage VR here. That's why we are taken IC is equal to J omega VR omega C, or omega is nothing but 2 pi FC. Okay. Now the sending end current is the phasor sum of both IR and IC. That is the thing. Current IS is a sum of IR plus IC. What is IC actually? IC is a pure capacitive current. Obviously, it is leading to the voltage VR by an angle of 90 degree. Is it very clear? No. Pure capacitive current is having a leading characteristics with the applied voltage. Applied voltage here is VR because the capacitance is connected at the load side. We are assumed that. Okay. So obviously IC is having 90 degree to the VR. So that some after IR, if we are going to add the IC, that is 90 degree with respect to the VR. So I have added IR plus IC. The sum of vector sum of that one is gives us the current IS. We can see that thing clearly. IR plus IC gives us the IS there. Okay. Or IS is nothing but IR plus IC. We are knowing IR cos phi r J sin phi r plus J 2 phi FC VR. After adding these things, J terms togetherly, we can write it as IS Z is equal to IS vector into R plus J XL. That is the voltage drop what we are having. Okay. IS is different and we are having the voltage drop is IS vector Z is equal to IS plus RJXL here. Now sending end voltage Vs is given by VR plus ISZ. We are knowing the previous things. Or VR is equal to IS plus RJXL. Here this equation is same as our previous short transmission line. But in previous case IS was same as IR. Here IS is not same as IR. Here IS is equal to IR plus IC. And voltage regulation is same Vs minus VR by VR into 100. Transmission efficiency is same as power delivered by power delivered plus losses into 100. Here some limitations of this method is given. The limitation is that the end condenser method is a solution of the median line. It is simple to work out the calculation, but it has got some drawbacks. That is, there is a considerable error, about 10% in calculation, because of the distributed capacitance has been assumed at lumped at the concentrated, because the distribution capacitance effect is taken at the end. So all the capacitive action is considered with the current voltage VR there. Okay, that is a problem here. And this method is overestimate the effect of the line capacitor. So it is assumes that overestimation. Okay, what actually capacitive effect is gives, it is gives the more than that effect. Okay, that's what this is the even the easiest method, but it has gives us the some error in calculation. Okay, anyhow, one problem we will see on this one. A medium single phase transmission line 100 km long has the following constant: resistance is per kilometer is 0.25 ohms, reactance per kilometer is 0.8 ohms, susceptance, that is the capacitance value, susceptance is given there for because 1 over 2 pi fc is that is given, that is 14 into 10 raised to minus 6 Siemens. Receiving end voltage is 66 kV. Assuming that the total capacitance of the line is localized at the receiving end alone, determine the sending end current, sending end voltage, regulation, supply power factor, and the line delivering 15,000 kilowatt at 0.8 power factor. I draw the phasor diagram. So before that, I want to finish this phasor diagram clearly. So once we got the VR, no, anyhow, we know that Vs is equal to VR plus ISZ. ISZ is nothing but IS plus R plus J IS into XL. So here you can be, it is very clear, ISR is in phase with IS only. ISXL is in phase with the, it is having 90 degree to the IS. So it is written 90 degree to the IS. So the sum of that is ISZ, and VR plus ISZ gives us the VS, and the angle between the IS and VS is nothing but phi s. That is the sending end power factors angle. Okay. The same problem we will continue with this one. Now all the values are given. Anyhow, per kilometer value is given. It is given that 100 kilometer line. So R value is 0.25 into 100. XL is 0.8 into 100. Y is 14 into 10 raised to minus 6 into 100. VR is 66 kV. Or IR is known as, first we find the load current here. 15 1000 because it is a single phase. Obviously directly will take 66,000 only, phase voltage only. Load is given 15,000 kilowatt. That's why 15,000 10 raised to 3 divided by 66 kV into 0.8 as the power factor. So you will get 284 amps. Cos phi is given 0.8, sin phi is 0.6 from that one. So we are writing VR is as it is, VR plus J0. Calculate IR using cos phi R and sin phi R. We will have a 284 is the its magnitude, and we will get the vector form. Once we got the IR, we need to find out the capacitance, that is JYVR, because susceptance is directly given. No, actually XC is nothing but 1 over 2 pi FC, or susceptance is nothing but 1 Y is equal to 1 over XC. So Y is same as 2 pi FC. So we will get ICS J92. So next things are very easy. IS is equal to IR plus IC. We will get the 227 minus J78 as IS, sending in current. If we want that magnitude, we will get the magnitude of that one. Voltage drop is to find out using the ISZ. We are knowing R and XL value, put the values, we will get the drop. Once we can get that ISZ, we need to find out the VS. VS is nothing but VR plus ISZ. So once we got the VS, we need to get the magnitude. So from that we will finding the regulations, and after finding the regulation, we need to find the angle of phi s. Okay, that is tan inverse of the VR's value, VSS value we need to put. So it is very clear that cos phi s is from 0.86 lagging. Okay, so you can solve the problem by your own. Anyhow, you are knowing the equations are same now. VS is same as VR plus ISZ. Only thing is here IS is equal to IC plus IR. So different equations are given. You try by your own. In the next class, we will see the nominal phi method. Thank you.